I asked ChatGPT, I was like, hey, so 100 picometers, how many elements on the periodic table have like an atomic diameter of less than that? And it said there were about 5. So
Wow.
for reference, I was thinking, okay, with diamond, perhaps we're not machining iron, but when I think of machining, I think of metal. So I just asked, okay, what is the diametric size of an iron, like an Fe atom? And it said it was about 250 or so picometers.
Picometers.
So we're
That
literally
is wow. You're
capable of
taking
movements,
atoms off.
basically.
Hello and welcome to the Being an Engineer podcast. Today we've got Sam Thomason, a bilingual sales and engineering professional with over 14 years of experience in CNC machinery, factory automation, robotics, and ultra-precision machining across the US, Japan, and Australia. He's currently National Sales Manager for Shibaura Machine's Nano Processing division, where he helps customers apply advanced machining platforms to demanding nano and micro precision applications. Sam is super passionate about helping manufacturers automate dull, dirty, and dangerous work so people can focus on higher value tasks. Sam, welcome to the show.
Oh, thank you very much, Aaron. Happy to be here.
So we didn't talk about this during the pre-show, but it just I know it was a question I wanted to ask and I kind of forgot. So you're bilingual. One of your languages is Australian, obviously.
Yeah,
What
is that saying?
what's the other one?
The other one would probably be, well, apart from sarcasm, which is kind of a dialect of Australian, would have to be Japanese. So I speak
Ah,
Japanese as well.
okay.
Use it every day at work.
And どこで
So,
日本語を学びましたか？
日本語話せれるのすごいですね。
ちょっとだけ。ほとんど
す
忘れました、
ごいですね。
もう。
いやいや、
ずっと前
そんなことあり
に日本に住んで
ません。
ました。
うまいんですよ。え
優しいですね。
いやいや、とんでもな
Um,
いです。Where in Japan did you learn
that's
your
fun.
Japanese?
I was in Hiroshima for a couple of years, way
Oh,
back in the
nice.
day. It was, yeah, back in my early 20s back there. But I don't get
Oh,
a
cool.
chance to speak Japanese very often, so that's fun. Thanks for letting me.
Wow. Like the JET program or something like that?
No, I was a missionary actually
Oh,
back
wow.
there.
Okay.
Yeah, preaching the
Interesting.
gospel. That's right, back in the
Well,
day. And
that's
how about you?
interesting.
How did you learn Japanese?
Well, I guess the start of it actually starts with missionaries on my side too. My parents were missionaries in Japan.
Oh, interesting.
So I was
Really?
actually born in Japan.
Wow.
Funnily enough, so my parents were missionaries living I think they were living in Tokyo at the time. My dad was
Okay.
ex-US Navy. So I was actually born in a US naval base in Yokosuka because it was cheaper than, the private hospitals. And that's not really, I guess I was kind of lying a bit there because that wasn't actually where I learnt my Japanese. We left when I was 1. So my Japanese at the time was probably more like goo goo gaga. But hadn't gotten to konnichiwa yet. But we moved to the States when I was about 1, where my dad is from, in Orlando, lived there for about 5 years, and then moved off to Australia, where I spent the rest of my upbringing. And I guess that's where the accent stuck as well, because believe it or not, I used to actually have a Southern, like an American accent when I was a little kid.
Really? Oh,
Yes. Yeah.
fascinating.
Yeah. My mum used to babysit a kid from Tennessee. And even though Florida isn't really synonymous with Southern accents, I picked up a Tennessee accent. And so all the home video of me from when I'm 5 is like, hey, mama, go take a bath. And, that sort of thing. And about a year later, it's like, g'day, mate, and it's sort
We're
of
so
where it is
pliable
now.
when we're young, huh?
I think so. Yeah. Unfortunately, I don't know if I can really change back. My dad, has been in Australia since then, and he still sounds roughly as American as the day, he arrived in 94.
Yeah.
He does use some Australian words, he does try to say g'day and whoop whoop and, things like that, here and there, but, the accent hasn't really come. And so I don't really have hope for myself there either.
Well, I
Um,
I grew up in Hawaii, and there's
oh,
definitely a particular accent there that I am so sad to say I've pretty much lost at this point. However, when I go back home, it does come out for sure. Or when I'm talking with other people from Hawaii, it tends to come back up. But otherwise, sadly, it is long gone at this point. Um, okay, but the Japanese, you
yep.
you did not learn it as a baby, as an infant
No.
there. So when
Yeah.
did you pick
Sorry.
that up?
The story continues. So I guess I learnt little bits and pieces growing up because as a child, like my parents, they both neither of them are Japanese, as you can probably tell by my complexion, but uh, mum and dad learnt enough Japanese to be roughly fluent. When they were doing missionary work over there. And so that was kind of their secret code. When I was a kid, when they wanted to speak in private in front of me, they would switch to Nihongo and I would be there saying, "What are you saying? What are you saying?" And they'd kind of just giggle. And so it became sort of a curiosity growing up. I want to know my parents' secret code. And so when I got into grade 6 in elementary school, they started, well, it was available at school. I started studying there and basically continued all the way through high school. That kind of got the basics down for me. But it wasn't really until I'd finished high school and I did a gap year in Japan with the Rotary Club, with Rotary International. They sent me over as a youth exchange student for a year, and I went to a Japanese high school in a semi-rural area named Ishikawa, um, out towards, if anybody knows Komatsu trucks, well, Komatsu is, right next door to the city of Kanazawa, which is near where I was, on the west side of Japan. Beautiful area. And lucky for me, not too many English speakers around, which was great
Yeah,
because
immersion.
I'm fairly lazy. Yeah. If I had been surrounded by English speakers, I probably wouldn't have picked up Japanese as I did. But lucky for me, nobody or very few people around me spoke English, which was fantastic. So yeah, I had the best year of my life. Went to
Oh,
a high school over
phenomenal.
there, came back to
Wow.
Australia after that, went back to college, and then I did my third year of uni, college, on exchange in Tokyo as well.
Okay.
And after that, I was kind of desperate to find a job in Japan. I was kind of dead set, okay, I want to find a job in Japan in that little sort of semi-rural area. And so at the end of college, I started shopping around for jobs, and just so happened that the best employer in town happened to be a Japanese machinery company called
Hmm.
Takamatsu Machinery, um, which is a lathe manufacturer that specializes in factory automation. And, I had studied communication and arts, so I was, on the exact opposite side of the planet from anything engineering related. Although I'd always been interested, it's interesting because from a young age, my favorite toy or toys, I should say, were always Legos. I love to build things, make things, tear them apart. But unfortunately, I was never any good at the math side of things. And I was to find out later in life that wasn't so much, I mean, I don't think I have a high natural aptitude, but I just didn't have any interest. There was never any sort of do this equation because it has this real effect in life. Um, so I still remember, for example, when I was uh, in high school and we had to do trig. And I remember doing my homework. My mom, as usual, was like, do your homework. And I was like, Mom, this is stupid. I'm not going to be an engineer. And this trig stuff, it's useless. It's just theoretical. I'm never going to use this in my life. Little did I know that further in life, I'd end up as an applications engineer. And trig, for example, I needed to do nose R calculations. When you're running a lathe, you need to make compensation for the fact that the nose of your tool is not actually a perfect edge. It's round. If you look at it um, microscopically, and you need to compensate for that when you're making chamfers and things like that. And so
Yeah.
I remember when my boss was teaching me, this math using just basic sine uh, and tangent calculations. I vividly remembered, me, yelling at mum saying, "I'm not going to need this in the future." But all of a sudden it was exciting. It was like, wow, I do this, formula and the numbers come out and I put it in the machine and
And it
then
works.
I press the button and it actually does what I want it to. This is awesome. And I kind of think perhaps if in my formative years, math and science in general had it been as sort of hands-on and, you do this to get this, if it had been set up in that way, I might have gone in a different direction. But yeah, I guess I had the assumption that I was more of a humanities guy. I liked history and language and aside from the fact that I always nerded out over the science fiction and the sciencey sort of stuff, and thought, well, I better play to my strengths. Studied that stuff, and then yeah, ended up getting a job for a CNC lathe manufacturer. And in the beginning, I naively, because I'd done sales all throughout college, I thought, okay, this is going to be easy. They're going to hand me a catalog, and I'll learn the catalog, learn the products up, and 3 months later, I'm going to be slinging CNC machines to the Japanese, like it's nothing. And fortunately for me, the company I was working for had different plans for me. They knew that you can't do that. You need to actually understand the product from the ground up. And so they started me off on the assembly line, building the machines. I worked on the factory floor, assembling machines for about a year. And then they said,
Wow.
okay, well, now you know how to build the machines. And I was like, great, can I go into sales? And like, no,
For a full
no,
year. So this wasn't like a superficial, figure out where a few bolts go. Like you really
no.
understand from the ground up how these machines
It
are built.
it was everything. Like, and I am so grateful. I will be grateful to Takamas Machinery for that experience till the day I die, because it really gave me a very hands-on and very grounded understanding of these, critical concepts that would, serve me well for the rest of my life, the rest of my career, I should say. It all started out, I remember my first job was just leveling machines. We'd have the machine bed with nothing on it before we put, the saddle and the slides on, and have to just get down there with the spirit level and the wrench and, make sure it's perfectly level, and pick, flecks of paint, off the moving slides, and very, very menial sort of stuff before we moved on to the more complex sort of stuff. Very kind of, Karate Kid, washing the windows sort of thing. Part
Wax
of it, I
on,
think,
wax
was
off.
wax on, wax off. But it was good because I think it also, it created some humility as well, and some appreciation
Hmm.
for the little things. Like, I'll mention cleaning the slides. Like, I'll never forget, one day because before we put, for example, the X-axis motor and Z-axis motor on top of the slides on the lathe, um, you have this sort of mirror finish, very nicely ground surface. And you need to make sure before any of that goes on, or for example, the ball screw that goes sort of underneath it, before those get clamped down, it must be spotless, because we had to ensure that ball screw was through, along its shaft to within about 5 micron. And if even so much as a fleck of dust, got under that unit that you bolted down, you need to use a torque wrench and get it perfectly torqued down, it wouldn't work. And I remember one day spending hours, I'm sort of clamping down, with the torque wrench, and you have to adjust it because, you tighten it too much, and, the ball screw goes this way or that way. And no matter what I did, I could not get it right. And my boss at the time, he was like, Sam, just rip it up, start again. And I was like, no, I've spent hours on this. He's like, do it. And, I was kind of grumbling, under my voice, took it off, and lo and behold, it seems there was a speck of dust, clean it off, work like a charm. And I
Right.
think I finished that
Wow.
job at about 10:30 at night. The only lights in the factory left on were the ones, over my little workstation.
Yeah.
But it was amazing character building stuff. And also it really, it forced that sort of attention to detail, particularly when precision is concerned. That, they would not accept if they said it needed to be below 5 micron, it couldn't be 5.5, it couldn't be 6, couldn't be 5.1, it had to be like 4.9 or less. And even that was really pushing it. And but that's how you end up with fantastic machines. And so after a year of that, I wanted to do sales. They're like, no, no, you know how to make the machines, you don't know how to use them. And so I was
No
like, oh,
way.
okay.
Wow.
And so
That's
they
an
put me into
intense training
applications.
program.
Yeah. And the
Wow,
crazy thing was,
speaks
oh,
hugely
sorry.
to the company, right? Like, I mean,
Yeah.
most companies, you're a sales guy. They want to get you selling. That's the revenue that you're going to bring in. They just
Hmm.
want to throw you into sales real quick. They spent, I guess, years or at least over a year training
Yeah.
you so deeply that that just says a lot about the company.
And most good Japanese machine builders, like I know Shibaura, who I work for right now, they do the same thing. The amazing thing is a lot of these companies in Japan, even if they intend to send you into a non-related field, like, I knew guys that ended up in marketing that they probably wouldn't have spent a year, but they had them in on the floor for at least 6 months, because they wanted them to have a real, nuts and bolts sort of understanding of what they were
Yeah.
working with,
Yeah.
at a
That's
very
so
deep
great.
level.
Huh.
Oh, it was
I love
fantastic.
that. Yeah.
Um,
And I love the fact that a speck of dust caused that many problems because it just speaks to the level of precision that is inherent in
mhm.
these machines.
It's
Wow.
amazing how, and that'll maybe tie in later when we start talking about nano machining, which is even another level on top of that. Um, how the world of microns is mind blowing enough, where a speck of dust can throw you off, and then you get into nano machining and just
Well,
it's
let's
insane.
dive into that. Yeah,
Yeah.
let's get into it. So, nano machining, I don't know anything about nano machining. I'm really excited to learn about that from you. There are a couple of other terms that I have written down here, diamond turning and
Yeah.
hard milling that I'm also not familiar with. Diamond turning, I can kind of guess maybe what that
Yeah.
is, but hard milling, I'm not really sure what that means. If you could talk a little bit about those terms and what they mean in the world of precision manufacturing.
Absolutely. So these are, I'm fairly new to this as well. I started this position in January, but I'm I absolutely love it. Having been sort of a machinery nerd before, this is like the creme de la creme of precision. So diamond turning, maybe I'll start out with that. And probably also good to mention aspheric grinding because they both kind of go together. They're generally machining methods used for creating optical surfaces. So, and when I say optical surfaces, I'm generally referring to like lenses. So camera lenses, um, and like your DSLR, or maybe the molds to make those lenses. So, for example, we make the ULC and ULG line of diamond turning and aspheric grinding machines. Um, the reason they call it diamond turning is typically, well, very simply, you have a monocrystalline diamond tool that you use to machine, typically like a nickel plated surface, or another usually non-ferric metal if it's a diamond tool. Although you can actually machine ferric materials if you're using ultrasound based tooling, but usually
You said
diamonds are
ferric
ferric.
materials?
So just things with iron in them. So steel, iron, anything that's related to iron, typically doesn't go too well with diamond tools. So because there is carbon in steel or even low carbon steels, and obviously diamond is effectively a compressed carbon. Um, you get issues machining wise when you try to machine one with the other. Um, so a lot of the time when you look at diamond turning, you're looking at materials that are non-ferric. Um, One of the most common ones we would see on our side would be like nickel plated materials. So we'll take like a stainless steel, we'll cover it in like a nickel plating, and then we will use a very special lathe, so a diamond turning lathe, to turn the shape that you want for the lens mold. Um, and where diamond turning, I suppose there are probably elements of it out in the world that are less precise. But at least what we do at Shibaura, and this is the mind blowing part. So I was going to build up to this, but I think I'll just jump straight into the crazy side of it. So our ULG machine, we were talking about 5 micron before with my background in Takamas. So the ULG, um, it's programmed in 100 picometer increments.
I
So
can't even
I know,
conceptualize
right?
what that means.
It's funny. My first week on the job, they're telling me about this, and I'm like, wait. because my colleagues are Japanese, and so we mainly converse in Japanese, and that works out well most of the time. But I remember stopping and thinking, wait, am I translating this wrong in my head? Am I off by like a zero or two? And then I got them to write it down on paper, and I'm like, you serious? You can actually program a machine to move at this level? Because a picometer, to put it, because I had to look it up afterwards, like, I'd never gone anywhere close to that. So to put it in reference, and I apologize to our imperial folks out there, I'm going to be talking in metric, but effectively a micron is, if you take a millimeter, because we can probably all imagine, millimeter, we put our thumbs together, and it's, hold your thumbs about as close together as you can without touching them, and you're roughly at a millimeter there. You divide that in 1,000 pieces, and you've got a micron. Now, if we take that micron, we divide it in another 1,000 pieces, we've got a nanometer. For reference, like a strand of DNA is about 1 nanometer. Most bacteria are about 1 to 5 microns in diameter. So once you go down to that, single micron level, we're talking about like literally the microbial, like bacteria level size of stuff. So microns are not to be snuffed at all. We're talking very, very small. So when we get into nanometers, 1 nanometer is about the size of a strand of DNA. Our UVM mill, which is a milling machine, actually moves in 10 nanometer increments, which is still like, levels of magnitude
Wild.
above anything I'd ever,
Yeah.
laid my eyes on before. And then our diamond turning and ULG machine, 100 picometers. So basically a picometer is 1/1000th of a nanometer. So I guess, 100 picometers is 0.1 nanometers. So it's a fraction, a tenth of a nanometer. And for reference, because I was like, how do I reference picometers? Like, it doesn't even make sense. And
down to an atom or something?
so actually that's exactly where I went. I asked ChatGPT, I was like, hey, so 100 picometers, how many elements on the periodic table have like an atomic diameter of less than that? And it said there were about 5. So
Wow.
for reference, like I was thinking, okay, with diamond, perhaps we're not machining iron, but when I think of machining, I think of metal. So I just asked, okay, what is the diametric size of an iron, like an Fe atom? And it said it was about 250 or so picometers. So we're literally
That is wild.
capable
You're
of
taking
movements.
atoms off.
Basically. So obviously that's the level of precision that we can move things in. The tooling is obviously going to be bigger than that.
Yeah.
And when you introduce things like, compounding error from, tool holders or, work holding and all that, you're not actually, as any machinist would know, just because a machine is capable of indexing in a particular, level of precision doesn't mean you're going to be able to machine to that level. But probably the best example I can give is if you've got one of these in your pocket, an iPhone, we made the lens molds for your iPhone camera on that machine. And the molds have a form accuracy of 30 nanometers on those. So there are a few
incredible.
things out there that are more precise than that. Like the only thing I can think of is like ASML lithography, where currently I think NVIDIA and others are making 2 nanometer with chips and things like that. So they're using light in that case. We're doing things, managing to actually create surfaces to within 30 nanometers mechanically.
Yeah.
Which that's why I love this job. I remember, just first couple of weeks, I just had this like, I thought my jaw was going to dislocate because, I was learning more and more about this world that had existed around me. I mean, we all have, a mobile phone in our pocket. We all live amongst technologies that really rely on this sort of thing, especially when it comes to optics. Our cars all have cameras in them. Our phones have cameras. All of this stuff is very critical in the world we live in nowadays. But I had no idea that level of machining was possible. until I started this job in January. So,
Tell me a
um,
little bit about the control system in these machines. I mean, it it can't just be any off-the-shelf motor and PLC code to run this thing. It's got to be a pretty unique control system, right?
that's a very good question. That's I can tell you you have an engineering background because that was one of the first questions I asked. I was like, how is this possible? Like, how do you do this? What I think the first question I asked was like, what sort of ball screws are you using? And my boss, because I guess he's been in this world for about 30 years, he looked at me almost with disgust. He's like, ball screws? Ball screws? What sort of a peasant thing is that?
We're not animals here.
I know. And then I came to learn about how, the control mechanism. So we don't use ball screws, we use linear motors. Um, and I guess Shibaura has been developing this technology over decades. So I'm part of a team called the Nano Processing division. And we specialize in generally, these super precise machines, not just lathes and machining centers, but also like glass molding presses. So, we'll make the molds, your glass lenses on one of those, diamond turning machines or spheric grinding machines. And then those molds will go into a glass mold press or, an injection molding machine if it's plastic. We sell all that stuff as well as specialty machines for making polygon mirrors that you use in LiDAR, slicers that are used for like fiber guides for, very, very useful in data centers now that they want to move, those fiber optical signals closer to the chips. So semiconductor stuff as well. Our team was actually basically started up in 1978 in Japan to support Toshiba's semiconductor business, because Shibaura is basically the Shiba part of the Toshiba name. So we all know Toshiba,
Okay. Yeah.
and we're the Shiba in Toshiba, basically. So the machine arm, I guess you could say, in the nano processing team kind of came about when Toshiba's semiconductor business was starting to grow. And there were all these machines that, the eggheads, designing the semiconductors wanted that just did not exist in the world. And so they started our team to basically create a whole bunch of technology to support the semiconductor industry initially. Now we're, much broader. We support, everything from headlamp molds and automotive to, aerospace parts, rocket nozzles and other sort of parts that require high precision. But initially created to support the semiconductor industry for Toshiba.
Fascinating.
Um, that's kind of how I suppose we ended up in this space.
So what industries or applications are most common for nanomachining? We talked about optics, right?
Yep.
Lenses primarily, semiconductor you just mentioned. Are there any other very common applications where this technology is used?
So I think the one I mentioned briefly before, like headlamp molds. Um, so our UVM machining center is very popular, especially in Asia, for creating headlamp molds. The reason being that headlamp molds, even though they're, not quite as maybe sexy as a camera mold, still require a very, very well finished surface for the mold. Any imperfection in that molded surface is going to end up, on the plastic part that is molded, and you're going to end up with headlamps that aren't quite as shiny or, don't throw the light as well. And so where we get a lot of our business there is the fact that there are obviously lots of other ways to machine these with more conventional machining centers, but they usually require a lot of polishing. So after everything gets machined out, some poor bugger with a rag or, Scotch-Brite basically has to go to town, rubbing, this mold until it's, has a perfect mirror finish. And in some cases, like we recently did a job for very, very large automotive company, second tier supplier, where they were using a pretty high end machining center, but it was a standard ball bearing sort of linear, ball screw style machine. And they had to spend 8 hours per mold just manually polishing And we managed to get that down to about 40 minutes. So in that particular case, we didn't eliminate it completely, but we got rid of over 7 hours of manual work.
That's huge.
And
Yeah.
it's interesting because that's actually where I think a lot of the business is for us now. Like it's very rare that you actually have a customer that says, on their drawing, we need something that, requires like a positional tolerance of, half a micron or, something like that. It exists, but it's very rare, very few and far between. One of the biggest advantages we get by having extreme control over our tools is we can machine a part with such a good finish that you end up with a mirror finish. You don't have to do any, post production work or very little. And it kind of rolls into, you mentioned, earlier, one of the things that I'm passionate about is relieving or reducing, dull, dirty, and dangerous work. And manual polish is just an insanely tedious job. Not only tedious and, it results in all sorts of RSI, carpal tunnel injuries and things like that. But it's very hard to find because it's funny. You think of polishing, you think that's a low skilled job. To do it properly and consistently where you're not over polishing here and there, especially if you're trying to hold very, very tight tolerances, very hard to polish it without actually over polishing and ruining what you're making. And so it's a very highly skilled position, but very tedious at the same time. And those two things together mean very, very hard to find people that actually want to do the job.
Yeah, I can imagine like sitting there trying to polish something for 8 hours every day. That would be a really, physically demanding job, right?
Oh,
Because you're
yeah.
having to apply some amount of pressure the whole time,
Yes.
evenly, consistently across whatever this surface is. I think that would actually be a really difficult job.
Oh, definitely. And sometimes dangerous too, depending on what you're polishing. You're obviously creating small particles. You're probably breathing them in. If you're doing it once or twice, it might not be a big deal. But if that's your day job, it's probably not great for your lungs either,
Yeah.
depending on what you happen to be polishing. So um, it's one of those jobs where I think, everybody I think is better off if we can automate, the lion's share of that away.
Yeah.
Humans are better off doing more human tasks.
Right.
I think, not to
So,
diminish the importance, but yeah.
of course, yeah. If I were to walk onto a factory floor with some of these, ultra precision machines, would I recognize them? Like, would I walk up and say, "Yeah, this is a lathe. This is a CNC machining center," or does the form factor of these ultra precision machines are they very different from more traditional machines?
So at least our machines, they look very similar to, many machines, especially, for example, our UVM mill, the one that we use, for making those headlamp molds and things like that, just looks like a vertical mill. That's
Okay.
that's why I remember when I first, you know, before I started the job, I looked on the website and I was like, oh, it's just a vertical mill, boring.
Sounds
um,
like a marketing opportunity there.
well, I'm actually still trying to figure that one out because it's a machine that doesn't really pop out at you, visually.
Yeah.
Like prior to this, I also did a lot of work with robotics, and when you have robots at a trade show, they're jumping around all over you've got movement, and movement catches the eye. As humans, we're kind of just designed to pick up on movement, um, and our machines, by their very nature, they don't move a whole lot. They're very, very small movements by definition, typically. And so at a glance, nothing sexy is really going on. But uh, if you know what's going on under the hood, it's quite incredible, because, we're using linear motors, as you said, very special ones that we make in-house that we've developed technology for, particularly through the semiconductor industry for a long time, as well as you have a spindle. That's the other important part of the if we talk about a mill, you have a spindle, you have slides. That all looks very similar at a glance, but the spindle, this is one that blew me away when I started the job too. We use aerostatic spindles, so there's no ball bearings in the spindle. So the spindle shaft, the bit that actually does the spinning part of the spindle, levitates in air.
It's
So
This is black
There's
magic.
a kind of, yeah. It's funny. Now you don't. The crazy thing is you don't even notice it because it's basically aerostatically held. If you can imagine, the inside of the spindle unit has pores, tiny little pores, almost like your skin, that has air blasted, in equilibrium to hold that spindle shaft perfectly, in the center,
It sounds like an
up
air
and down.
bearing.
That's exactly what it is. It's an air bearing.
Okay. Okay.
It's an aerostatic spindle. So it's a air bearing based spindle, has like a 10 micron film of air that sort of encompasses the tool. And then we
Wow.
use induction magnets to rotate it. So there's
Mm,
no physical contact apart from the actual workpiece that's being machined.
okay.
Same goes with our diamond turning machines. They use aerostatic spindles as well. Um, and for example, with the mill, we get a run out on that spindle of less than 10 nanometers.
Oh,
And you end up
10
with a profile.
nanometers.
Yeah.
That is
So
so cool.
when it runs, you can't see it. Like when my first week on the job, I went to have a look at the machine, and we had our applications guy, Casey, out by the machine. I was like, Casey, okay, can you rev the spindle up for me? I want to see this thing. You said it goes up to 60,000. Let's see it. And he's like, oh, Sam, it's already on. I'm like, what? Because I'd never encountered a machine that went up to 60,000 RPM before, but I imagine it would be like rip roaring loud. And when I got there, it was already at 40. He had it idling at 40,000.
Oh,
And I'm kind of like, can you turn it on? And he's like, it's already running at 40. And I look closely. And the funny thing is, I could see a tool. And then I looked closely and I realized that I couldn't make out any flutes. Usually, if you've got an end mill or a
yeah.
drill, you can sort of
Yeah.
see the individual flutes. I realized that it was just like a cylinder.
Wow.
Wasn't even really a blur because it was rotating so, you know, perfectly
Yeah.
that your eye doesn't even really pick up on the fact that it's rotating. Kind of dangerous. And it also makes almost no noise. When he
Oh my
jacked it up to
gosh.
60, you could kind of hear the air purge, that holds it does, go up, and you can hear a hiss of air. But because there's no physical contact, it's almost silent, and just blew me away. It really did. It's interesting. When I started this job, prior to that, I'd been working in sort of AI robotics for a little while, and I was kind of concerned that, is regular machining really going to sort of, scratch the itch, the nerd itch? And it floored me, in the first week that, we have spindles without bearings, we have slides without ball screws, we're moving in 10 nanometer increments on the mill, and then, the 0.1 nanometer increments on the lathe. Um, and I guess my next challenge was, how do you actually use this in the real world? Which was your question earlier. Optics, lenses, things like that are probably the main one that comes to mind. But with machining, um, there are a lot of molds out there. So just about, a lot of the plastic um, stuff, plastic stuff, metal stuff, a lot of it originates in a mold of some sort if it's being mass produced. And the molding process, well, you generally have to use very, very hard metal of some sort, some sort of hardened tool steel, or in some cases, carbide, like tungsten carbide, which is, much harder still. And you don't only have the precision aspect to contend with, you also have the fact that it's really hard to machine those sorts of things. And where this machine and the tolerances really come into play, like if we use carbide as an example, um, if you want to make, let's say you want to make bevel gears, or you want to make powdered metal, mass produce, planetary gears, things like that, you generally are going to need a carbide mold or die for that. And carbide, well, is already, a very expensive material, gone up in price quite a lot this year. But usually it's so damn hard that, and this is where hard milling comes into play, um, people usually just assume you don't mill this. You don't turn it. It's like cutting with an eraser. We have to use EDM, electronic discharge machining, for that. And nothing wrong with EDM, but EDM is a very laborious and time-consuming process where you literally, if we're talking about sinker EDM, for example, you have to basically machine out a graphite probe of the shape that you want. So you have to, put that in a mill, put your graphite in a mill it all out, in the opposite shape that you want, basically. And then you put that in your EDM machine, and then you put the material that you want to machine in there, and it basically just zaps it until you end up with the shape that you want. So you've got multiple processes there, and then after you've zapped it into the shape you want, there's usually this white layer left over that you have to then go and polish off afterwards. And that can sometimes take quite a bit of time to get rid of. And then there's the fact that EDM, by its very nature, you're basically using lightning to machine something. So those little, lightning forks occasionally will go deep into the mold that you're creating and create a microfracture. And sometimes it won't be in a critical location. You'll be fine. The mold will last as long as you expect it to. Other times, your mold is going to die, much sooner than you would expect. If you machine something, then you don't have those little forks of lightning going through the part, and you don't end up with that fracturing, provided you machine it properly. The problem is with something like carbide, where it's like super, super hard and brittle. If you take too deep a depth of cut, and when I say too deep, I mean like if you take more than a micron at a time off of that material as your end mill, a tool is rotating towards it, you're going to crack it instead of cut it. We have something called the plastic deformation line, where basically anything below that, you're cutting it as you would imagine, cutting through, butter or something like that at the microscopic level. And then anything over that, you're basically just fracturing it off, which is, obviously not good for the material and not good for your tools either, because that everything has an equal and opposite reaction. You're going to damage those tools, and that's why usually people would not mill materials like that. So by having a machine that you can move in increments of 10 nanometers, we can actually hit that sweet spot, that Goldilocks zone for machining things like carbide. And that allows us to hard mill things that you usually wouldn't be able to. And so that's,
so the term,
yeah.
sorry to interrupt, the term
No,
hard
no,
milling
please.
simply refers to machining a very hard material like carbide. Is that
Yes,
accurate?
that's right.
Okay.
Yes. And also because it's hard to do. I think that's the joke. But yeah, it refers to hardened materials.
Okay,
So
great.
carbide, tool steels, things like that. Um,
How about designing for these processes? I mean, uh, I've put together a lot of drawings in my time, and a drawing is second nature at this point, right? I put my dimensions on there, put some tolerances on there, material call out, maybe a surface finish. Is it basically the same thing to design for like a nano precision machining process, or are there like specific DFM principles that need to be followed when designing for these things and
mm.
calling them out on the manufacturing documentation?
So I think, in essence, I guess you could say it sort of scales, but there are some big differences. So, for example, and these are probably more on the machinist side than the design side. Like, obviously,
Okay.
designers should obviously keep in mind the fact that every time you increase those tolerances on that drawing, it's going to add cost because, eh, if you don't need those tolerances, then maybe the job shop you job it out to can do it on a Haas instead of a Yazda, something like that. Depending on the tolerances, you don't need as expensive a machine um, for that task. And the same goes with nano machining. I guess the first question is, do you really need it to be this accurate? And a lot of the time, at least for our machines, that answer is usually there are obviously some applications where positional accuracy or things like that need to be very tight. Um, anything optical, for example, and that's where we win business just on the pure accuracy side. But I think when it comes to hardened materials, and this is where we're not necessarily talking about the dimensional accuracy as much as just the nature of the material itself. that you're requesting to be worked with, you need to take a lot of extra things into account. Obviously, if a material is hardened, like if, let's say you gave me a part with tight tolerance that was in regular carbon steel, I'm likely going to be able to put that on a more standard mill, do a rough cut and then a finished cut with fairly standard tools. And that's going to be the end of the process. I'm not going to have to worry about things like, is the tool out of the box, a new tool, is it actually dimensionally accurate, within, a micron or two? If you're trying to hold, say, 50 micron or, like 2 or 3 thou, those things are less important. If you are trying to hold very tight tolerances, and also you're trying to hold those tolerances, especially in hard material, everything is your enemy. So heat, for example, as things heat up, if things elongate by a few micron or like a tenth or so, yeah, if you're trying to hold a few thou, probably not the end of the world. If you're trying to hold, half a tenth or, a micron or two, that's your entire tolerance. Gone. So I guess you could say that the things that do need to be considered tend to lean more towards less from the design. I guess the question is, do you need it? Once you've gone beyond that and you're like, yes, I do need these tolerances for whatever reason. The question then goes to, okay, well, do I have the right tools? Well, the right, machine for this, and do I have the right tools for this as well? And do I have the right software to write the paths and the passes correctly for this? Have I considered things like heat, tool wear? As you can imagine, as a tool wears as well, if it's wearing by a few micron, no big deal. If you're holding, a few thou, if you're holding a few tenths, that's, game over. So
Does the tooling look the same as you would see in traditional CNC machining? Is it, or is the tooling very, very specialized as well?
So usually the tools that we use in our machines, they look similar. They're just smaller. They look a bit like dental tools for the most part. For us, usually a large tool would be, 6 mil diameter or something like that. Like about, quarter inch would be on the large side. I mean, we're actually releasing a machine at the end of the year that's good to about 12 mil or so. But usually we work in the realm of finishing. So, we're not doing rough work or, rough tasks. There are plenty of machines out there for that. We're usually working with smaller tools at very high RPM. The tools themselves, though, they look similar, but they're usually incorporating materials that you usually wouldn't use. So, for example, if we're machining carbide, we need to use a diamond-coated carbide tool, for example, for that. Or in some cases, we might be using not CVM. I'm just trying to have a brain fart. Sorry. PCD, sorry. So PCD tooling, polycrystalline diamond composite tool for that. And those are tools you probably wouldn't use too often just doing regular sort of machining. Like, polycrystalline diamond tools as well. I think we're all familiar with diamond, but probably not too many machinists work with, like single edge, diamond turning holders and end mills and things like that. So they don't look crazy, but yeah, they're usually a bit more specialist.
So I imagine the machining is very expensive because you're using a very expensive machine and it's not removing much material, probably not very big parts also, but are these machines commonly used on like finishing single parts, or is it almost universally they're finishing molds that then end up making, hundreds of thousands or millions of parts?
That's a really, really valid question. A lot of the time it is molding and tooling and things that are used to make other things, if you catch my drift. So it'll be maybe a press stamp for a press, that is then used to mass produce things. plastic or glass mold for making lenses, but we do occasionally make individual parts. One application that comes to mind, like in aerospace, sometimes there are certain types of nozzles for, say, rockets or, jets that require extremely hard substances like Inconel to have very, very tiny angled holes put
Hmm.
into them
Okay.
um, for, fuel injection, that sort of thing. Same in semiconductor. There's a part called a shower head, which is, well, not a particularly inventive name because it looks like a shower. It's literally like a round disc that just has like, a few thousand very, very small holes drilled in, usually some sort of silicone carbonate or like a hard silicon substance. And usually we're talking like, like 0.2 mil or, very, very, very small, but, relatively long drills going
Okay.
through
Yeah.
those.
Yeah.
So they require a very stable machining process to work. So you don't, snap the drill
Yeah.
instantly, sort of thing. Um,
Um, this is fascinating stuff. I've learned a lot here, and I can just imagine when you started this job, just like a kid in a candy store, right?
oh yeah,
That's
still am.
amazing. Yeah, right. Still, I'm sure. I'm sure.
Yeah,
I've one more question for you, and then we'll kind of wrap things up here.
sure.
I'm always curious about cost. So you
Mm,
go out and you buy, a Bridgeport manual CNC, not CNC, just a milling machine, right? Maybe it's, I
yeah,
don't know, 20 grand or something like that, 10, 20 grand, maybe it's used, whatever. You get a CNC machine, maybe you're up at, 100, 150,000, somewhere in that range. What does it cost for one of these nano CNC machining machines? Like, I
yep.
imagine they're
So
not
usually,
affordable.
no. Well, I mean,
That's not the
at the
right
end
way
of the
to say
day,
it. They're,
yeah, it always
yeah,
depends on what your
commercially
goal
they
is.
justify
Like
themselves, of course.
if you're just looking to make some hubcaps, for your car or something like that,
Yeah,
yeah, probably not the best idea. Um, Stick with the Bridgeport or something like that. But um, usually we'd be starting around the 450K mark or
okay,
somewhere thereabouts.
okay, yeah,
Um, it's interesting because obviously it all depends on what the job you have, is.
yeah,
But if we go back to say the example of polishing, if you're making molds or you require molds, sometimes it's a case of it's a mold shop, they make molds, or it might be a place that does a lot of molding and they want to actually do molding in house. Um, you could say, Sam, I can buy a really good mill for 400K for like a really high end mill. That's a lot more. But if you consider the fact that they're probably buying a mill and an EDM machine, and they're hiring a guy to polish as well, if we can eliminate those things, or even, two of those three things,
yeah.
it actually turns out to be a bargain. Not to mention that one of the things that the machine we recently released does is, as I mentioned before, when you're doing things, especially with things like Carbide, you need to hold very tight tolerances. Everything is your enemy. Heat is your enemy. Tool wear is your enemy. It's all fighting against you. We actually have a camera built into our machine that gauges the tool before it goes into the cut. And so even if you buy a really good tool, it's probably going to be off by, a tenth or so. Um, and your CAD CAM software is going to assume that it's just this perfect semicircle, if it's like a ball nose end mill. In reality, it's kind of this old, raspy looking thing under a microscope. And so our machine has this system called FormEye, which it's another one of those things that just blew my mind, having done a lot of manual offsets in my life, because what it does is it puts the tool in front of this special camera. It rotates the tool. It takes 91 different pictures of that tool, and it creates a topography of that tool. And then it offsets all of your tool vectors based on the
Oh
exact
man,
topography of your tool down to the 10 nanometer level.
that is
So,
cool. Wow.
that nose compensation I mentioned before, that I had to do, it's like that times 91, except accurate to, about 10 nanometers. And so no matter which way you attack with, it knows the optimal compensation to give to that
Yeah,
tool. And the same goes
yeah.
with tool wear, heat. So we're trying to
Oh
automate
man.
that really difficult part, which means that, a regular average machinist can, with a bit of training, do things that were usually reserved for like a godlike machinist in the past that had to
Wow.
have all of that going in his head. And a lot of that
Yeah.
happened to be guesswork anyway. So it is
Wow.
actually a bargain. I'm sorry, the salesman side of me is coming out, but $450K when we actually have those things going on, is because it's basically it's a mill, it's an EDM, it's a CMM,
Yeah.
kind of
You're
all
replacing
in
all
one.
those machines and the
Yes,
time for all those.
e-
Yeah.
exactly.
Yep.
So
Yep. No, I get it.
it's it's a not a cheap machine, but when you consider what it's doing, it's actually a bargain.
Yeah.
If you have the right application, obviously, you need to have that application to justify it.
Well,
Like all
Sam,
things.
thank you again so much for coming on the show here. I think I actually used, at least I read from my list, one question, and everything
Oh,
else
whoops.
just I think that's the sign of a really great interview, right? Because
Oh,
I didn't
thanks.
have to go back and refer to my notes. The conversation and the information that you were sharing was just so interesting, so fascinating that the
Oh,
questions
thank
just
you.
kind of automatically came out. So this was great. Thank you so much again for being on the show and sharing all this. I think everyone listening to it is going to be fascinated by just the the level of precision that you can achieve with these machines. Spectacular. Thank you again. Um,
Thanks, Shane.
so we'll wrap things up here, I guess. But any like final comments or anything? I'm sure there's plenty more that we could talk about. But anything else that you want to make sure gets into this episode before we wind this down?
Just if anybody out there is interested in giving this a try, especially if you're doing anything with mold die, or even if you have just a really tricky part, that you're just wondering like, hey, I wonder if we could do this. Give me a yell. I'm always happy to nerd out over this stuff. And if it looks like it's something worth pursuing, we usually do free test cuts. So we're willing to put our money where our mouth is. We don't expect you to believe us at face value. We'll actually, you give us the materials and the drawings, we'll make your part for you and take it from there. So
We'll do the black magic for
would
proof.
would love to, yeah, nerd out with anybody who wants to reach out over LinkedIn or email or anything else. Uh,
What's the best way for people to reach out to you?
I'd say like LinkedIn, just look me up, Sam Thomason, on LinkedIn, or free to email me at sthomason, that's STHOMASON, at Shibaura, that's SHIBAURA dash machine, MACHINE.com. And yeah, like I said, happy to just, if you have a question, I'm not going to pander you for a machine or anything like that. I'm always happy to just geek out. If you've got some questions or proposal, a what if sort of scenario, I love those as well. So,
Awesome.
yeah, give me a yell.
Super interesting, fascinating stuff, Sam. Thank you again so much for sharing with us today.
Thank you. Oh, my pleasure. Appreciate it, Aaron.
I'm Aaron Moncur, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing advanced manufacturing processes, automated machines, and custom fixtures, complemented with product design and R&D services, visit us at teampipeline.us. To join a vibrant community of engineers online, visit thewave.engineer. Thank you for listening.